So this is sheet 3, question 5D. And it says, show that Nick can land safely on the second ramp. Okay, so we've got the situation where when Nick is in this position, so when Nick is here, he's got an acceleration of -7. He's got a velocity of 9.22 going in that direction. But the minute he leaves the ramp, we now have a different set of circumstances. We have totally new rules happening. The minute he leaves the ramp, he's no longer touching the ramp. He is in the air, which means there's no friction, there's no weight force other than gravity, there's no normal reactive force because he's not on a surface to be pushing back. So what I'm going to consider is I have this velocity going in that direction, but if I consider I and J, the only acceleration that is happening is gravity, and that's in the J and it's negative. So let's call the acceleration with respect to T equal to -9.8 in the J. That is the only acceleration that's happening, which means the velocity is going to be the integral of -9.8 in the J, which is going to equal -9.8 T in the J plus some constant C. And there is a constant because I know that he's travelling at 9.22 metres per second at 45 degrees to the surface the minute he leaves here. I don't care what he was down there because this is the point. And I'm going to recast everything and I'm going to call this new position 0, 0, and I'm going to call this T equals 0 for the time that he is flying in the air. Okay, so I know that he has velocity in this direction at 9.22 and that's 45 degrees. So his V of 0, that is his velocity at time 0, will be 9.22 cos of 45 degrees in the I plus 9.22 sine of 45 degrees in the J, which on a calculator comes out to be 6.52 in the I plus 6.52 in the J, which means that when I'm looking at using this, my V of T is going to equal 6.52 in the I plus 6.52 minus 9.8 T in the J. And X of T will be the integral of all of that, which will be 6.52 T in the I plus 6.52 T minus 4.9 T squared in the J plus some constant D. But since I've said that I'm going to call this point here 0, 0, my D coordinate is 0 in the I plus 0 in the J, therefore X of T does equal all of this, 6.52 T in the I plus 6.52 T minus 4.9 T squared in the J. Now, I can show that he lands safely if the time that the J component is 0, so if I want to make the J component of X equal to 0, that will tell me the time that we're back at the point where it would land on the ramp. And if J was 0 when this was X value was bigger than 8, then the person has to land on the ramp. So what I'd like to do is I'd like to find the time when the J component is 0 of position. So when is J component equal to 0? So 6.52 T minus 4.9 T squared equals 0. and that's going to be at t equals 0 and t equals 1.33 seconds on a calculator. So if I put x of 1.33, I can find out where it is at that time, and I come up with 8.747 in the I plus 0 in the j. And since 8.77 will place your person there, he has to land on the ramp and not miss the ramp. Hope that logic makes sense. Since 8.747 is bigger than 8, therefore lands on the ramp. So that's part D. Part E says, find the horizontal distance between the top of the first ramp and where Nick lands on the second ramp, and give that to 2 decimal places. Okay, so what this question is asking is x. Notice it's labelled an x here in the original question. And x goes from when Nick leaves the first ramp and where he eventually lands on that ramp. So I'm going to call that x. So I'm interested in the coordinates of where the person lands. And where the person lands will be at x in the x-axis. And what will be the y-coordinate of where the person lands? Well, it's going to be, let me think about this. I've got this ramp, and I know that that is 30 degrees, and I know that that point there is at 8, 0, and this point here is at x something. And they gave me that 30 degrees so I can use it to create a right angle triangle. I know that this will be x minus 8, and that this y component, if I use my 30 degrees, the tan of 30 degrees will equal y on x minus 8. Therefore, y equals x minus 8, tan of 30 is root 3 on 3, or 1 on root 3. So it will be negative root 3 on 3, x minus 8. Since that magnitude is this, but of course I made this 0, 0, therefore this coordinate down here will be minus. So I could find the time when the person lands here and the x value by doing a simultaneous equation. And the simultaneous equation would be, if I set the I component of x of t equal to x, that is, find out by setting my I component of displacement equal to x. So that's going to be 6.52 t equals x. And set the j component of x of t equal to negative root 3 on 3 x minus 8, and solve for x and t. So that will give me, the j component will be, what is the j component? It will be 6.52 minus 4.9 t squared equal to negative root 3 on 3 x minus 8. Solve for x and t, and that on a calculator gives me two answers. X equals 4.24 and t equals 0.65, and that's no good because it has to be bigger than 8. It also gives me x equals 9.439 and t equals 1.44, which I do like. So therefore, they will land at a value of x equaling 9.44 meters, and that's the horizontal distance across. And lastly, find the minimum angle between the first gate and the ground such that Nick can safely land. Okay, so now I have this as being theta, and that's 30 degrees, but it doesn't really matter what that is, because what I would like to do is I would like to find the angle of theta that has Nick landing exactly there. So landing at 8, 0. Because if I take a theta value which is smaller, I'll need to double check whether I want bigger or smaller. So what I would like to do is I would like x of t to equal so the 6.52 came from this. So I need to have 9.22 cos of theta in the I and 9.22 sine of theta in the j. So therefore my x of t is going to be 9.22 cos of theta t in the I plus 9.22 sine of theta t minus 4.9 t squared in the j. And I would like to find 9.22 cos of theta times t equals to 8, because my x coordinate has to be 8. And I need 9.22 sine of theta t minus 4.9 t squared to equal 0. And I can solve that for t and theta in my simultaneous equations. And that gives me an angle of 56.39, or to one decimal place theta is 56.4. Now my big question is, do I want theta smaller than 56.4 so that it lands, or do I want theta to be bigger than 56.4 degrees for it to land here, for it to be a safe landing? And it's all governed by what's going to happen with my x. So this bit has to be equal to 8. Now cos of 0 is 1 and cos of 90 is 0. So therefore the bigger theta gets, the bigger the cos gets. So I want okay, when exploring this solution where I got 56.39, I get one answer of 56.39. But when I go over further, I get another answer of 33.63 to one decimal place, so 33.629, which is 33 two decimal places, 63 degrees. Now I know that 45 degrees is safe. Therefore, theta's got to be between 36.63 degrees and 56.4. So that's 6 to one decimal place. So that's going to be my range of theta that has me landing safely. When theta is smaller than this, then I can't land on the ramp. And when theta is bigger than this, I'm going to have a situation where he would land and not reach the second ramp. When it's smaller than 30 degrees, he's never going to get to the height to get up to this point. Therefore, theta has to be between 36.6 and 54.4 degrees.